Hi, my name is Nicholas Castillo, and I'm applying for a program in mathematics at the Courant Institute of Mathematical Sciences. Hope to get a PhD in pure math and enter academia. A little bit about myself: I grew up on the East Coast. I did my undergrad at NYU Poly. I got a Bachelor of Science in Mathematics, and I graduated in 2012. I then joined the Navy, was commissioned as an officer, spent a couple years on a submarine, and I've since gotten out. I've been out for about 2 months, and now I'm applying for grad school. So why do I want to get a PhD in math? Well, it's pretty simple. I get great joy from everything mathematical, from thinking about it, from problem solving, teaching it, and reading and learning about it. It's been there since I was young, through high school, college, and as well as in the Navy. In the Navy, I continue to learn. I learned general relativity, a little bit of classical field theory, Lagrangian Hamiltonian mechanics, and some other stuff. It's never enough. So today, I'm going to talk a little bit about complex analysis, which is my favorite subject. I love it because it's just such a broad spectrum of ideas and useful ideas and beautiful ideas. For the useful side, we have electrical engineering, phasors, Z transforms, Fourier transforms, Laplace transforms, Z transforms, Fourier series, and that purely comes from complex variables. And then on the abstract pure side, you have group theory, Möbius transformations, hyperbolic geometry, number theory, Riemann zeta function, gamma function, stereographic projection, just a huge plethora of ideas, wonderful ideas, and they all come from humble, simple beginnings, the complex numbers. So today I'm going to talk about conformal mapping, and as it relates to boundary value problems. So if you recall, a conformal map is an analytic function whose derivative is non-zero. So if we look over here, let's say we have a conformal mapping between two regions, simply connected regions, dz and dw. dw is let's say it's a disk, and let's also say that we have a scalar valued function phi on dw. It's real valued and it's harmonic, so del squared phi is equal to 0. So the wonderful thing about conformal maps is what it does to the boundary conditions, and what it does is it doesn't do anything. So we can study partial differential equations, or we can study Laplace equation in simple regions, and then if we can map those simple regions conformally to another more complicated region that we could never solve for it before, like otherwise, then we know the solutions in those more complicated regions, so long as it's conformal. So let's say we have our Dirichlet conditions, so we know the value of the function on the boundary. The boundary is equal to phi naught, and let's say we have the Normand conditions, which states that the normal derivative of the function on the boundary is equal to 0. So if we define this new function, big H, which would be a mapping from dz into R, via F, which is whose components are real and imaginary components are u and v, then H is also harmonic, and H also satisfies these boundary conditions. The value of H on the boundary is phi naught, and it also satisfies the Normand condition. So I'm going to talk about my favorite transformation real quick, the Joukowsky transformation. So in fluid dynamics, you can define this complex flow function whose real and imaginary components are potential function phi and stream function psi. This tells you the energy content of the fluid at a point. This tells you the direction in which the fluid is going to flow at the other point. So this conformal map, z plus 1 over z, will map a disk into the profile of an airplane wing. So using the same idea, if we study the flow the streamlines around a disk, I can then map that into the profile of an airplane wing, and I know the solution in this environment. And I can show that the pressure below, the lower pressure, is greater than the upper pressure. PL is greater than PU, and so we have lift. Thank you for your time. Really appreciate it, and I hope to attend Courant Institute. Thank you.